Right, the next section for chapter 11 is to talk about neutralization reactions. Neutralization reactions are reactions that occur when you have a strong acid and a strong base mixed together, and what you're left with in the end is a neutral mixture that is a mixture of water and a salt or an ionic compound. So this is very similar to writing precipitation reactions that we did back in 6, but in this case we're not going to have to worry about solubility. So our general reaction is you're always going to have a strong acid and a strong base, and you will always make water and a salt. So in this example we have our acid, it has the hydrogen ion on it, and we have our strong base with hydroxide ion. So the hydrogen and the hydroxide combine to make water. So the H with the OH is H2O. Then the anion from the acid and the cation from the base combine to make your ionic compound, which in this case, in this example, is sodium chloride. So when you're writing the formula for the ionic compound, you'll have to use your charges. So chloride ions are -1, sodium ions are +1, so it's a 1-to-1 ratio. So again, very similar to precipitation reactions, where you take half of each reactant and combine them to get your products. Again, here's some guidelines for writing neutralization reactions. One quick kind of shortcut is you want to see if you have equal amounts of hydrogen ions and hydroxide ions. You have to have equal amounts. If it's not 1-to-1 ratio just with formulas, then you can use this, you can make them equal by using a coefficient, or in a sense balancing your reaction. Your hydrogen ions along with your hydroxide ions are going to combine to make water. The number of water molecules is going to be equal to the number of hydrogen ions and hydroxide ions you have. So if you have 2 hydrogens and 2 hydroxides, you would make 2 waters. Then you have to figure out the charges on the ions that are left over, and you combine those to make your salt with the correct formula. And then again, you want to make sure your reaction is balanced. Here are a couple examples. So for this first one, we have HCl with magnesium hydroxide. So HCl is our acid, so that hydrogen ion along with the hydroxide ion from the base is going to make water. Now notice we have 1 hydrogen and we have 2 hydroxides. So I'm going to go ahead and put a 2 in front of the HCl. So now I have 2 hydrogens and 2 hydroxides, and that's going to produce 2 waters. H2O. Then I'm going to get my salt formula from what's left over. So I have chloride ions and magnesium ions. So chloride ions are in group 7, they're -1. Magnesium ions are in group 2, they're +2. So that means for every 1 magnesium, I'm going to need 2 chloride ions. The other way I can figure out that formula is I already know I have 2 chloride ions from the 2 HCl's, and I only have 1 magnesium from the 1 base. So my formula has to match that. So balancing as you go is helpful. If we look at the second, we have 2 hydrogen ions and 1 hydroxide ion. So I'm going to go ahead and put a 2 in front of the KOH. 2 hydroxides and 2 hydrogens. Again, we're going to make 2 waters. If I look at what we have left, we have SO4, sulfate, and potassium. If I use my balancing here, I have 1 sulfate and 2 potassiums, so that's K2, SO4. The other way I know that is potassium's in group 1, it's a +1 charge. Sulfate is a polyatomic, you can look it up, it's a -2 charge. So 2 potassiums for 1 sulfate. Let's go ahead and pause the video and see if you can do number 3. All right, if we take a look at number 3, we have 3 hydrogen ions and 2 hydroxide ions. So this 3 and 2 ratio we've seen before, we need to cross multiply. So we're going to have 2 of the acid molecules and 3 of the bases. So that gives me 6 hydrogens and 6 hydroxides, which means we're going to make 6 water molecules. Then if we look at the other half, we have phosphate and calcium. And this tells me I have 2 phosphates and 3 calciums. So if we write the products, that's Ca3, PO4, 2. Double check ourselves, calcium's in group 2, it's +2. Phosphate is a -3. So if we swap our charges, we get 3 calciums and 2 phosphates. One example of a neutralization reaction that you might encounter is taking antacids. So the acid in your stomach is hydrochloric acid, HCl. And if you have heartburn or an upset stomach, a lot of times that is due to having too much acid present. So to help get rid of that extra acid, you take antacids, which are bases. So you're doing a neutralization reaction between the HCl in your stomach and whatever antacid that you are taking. Here's a couple examples of the active ingredients in various antacids. So Alka-Seltzer has an active ingredient of, this is sodium bicarbonate, which is baking soda. It's a base. Gaviscon is aluminum hydroxide. So you have a Arrhenius base there as a hydroxide base. Maalox is aluminum hydroxide and magnesium hydroxide. Milk of magnesia is just magnesium hydroxide. Rolaids, calcium carbonate and magnesium hydroxide. And then Tums is calcium carbonate. Calcium carbonate is limestone. So if you're eating Tums, technically you're eating rocks, but it works. It's basic. So the problem here wants us to write the neutralization reaction between Gaviscon and our stomach acid. So Gaviscon is the aluminum hydroxide. Our acid is the HCl. So we have 3 hydroxides and only 1 acidic hydrogen, so we're going to need 3 HCl molecules. That will give us 3 waters. And then what we have left is 3 Cls and 1 aluminum. So we've got AlCl3. And aluminum is +3, chloride is -1, so that formula makes sense. Here's another example of a neutralization reaction that you might have seen before. This is baking soda and vinegar. So you've ever made a volcano. So baking soda is sodium bicarbonate and vinegar is acetic acid we have here. In this case, what we're making is carbon dioxide, which are the bubbles that form, water, and here is the salt that is made. Notice in this case we're making carbon dioxide in addition to the water and the salt that we've seen for other neutralization reactions. So the reason this is different is we have a weak acid and a weak base, whereas the neutralization reactions we've seen and that we're going to write actual equations for is between a strong acid and a strong base.